Okay, population growth is the title, and we're going to be looking at two types: exponential versus logistic. So here's something I'm noticing right off the bat: there is no linear. There is no such thing as linear population growth. So that's kind of interesting. Why not? Why would there not be linear? So here's the reason. If you take, let's say, like a little, let's just pretend it's like a circle, and every 10 seconds, this circle replicates itself. What do you have? So 10 seconds later, we have two. 10 seconds later, we have four. 10 seconds later, we have eight, because each single one of these is dividing, right? And then 10 seconds later, we have 16. Oh my gosh, this is going to get crazy really fast, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, and so on and so forth. So if you graphed this out, this exponential growth, which by the way, isn't this just how like a bacterial colony? Do you guys remember when we smeared the little bacteria on those agar plates and we put them in the incubator? Like you guys took just the tiniest amount, right? Just the tiniest amount of bacteria. And then within 24 hours, your bacteria you had a full blown colony. I don't know if you recall that, but you had to take that little wand. Remember, it told you to find like 2 to 3 well isolated colonies. So you took the little wand and then you mixed it in the liquid. And then after that, you inoculated the plate. And with just a short period of time later, within 24 hours, your bacteria had formed full blown colonies. So, how does it replicate itself so quickly? It's just this concept of exponential growth, right? When a bacteria replicates itself and then that bacteria replicates itself, if you graph that population over time, you get what's called like that's an exponential growth curve, or also known as a J curve. But anyway, there is a lot of panic about this with humans, actually. Like, I don't think there is so much anymore, interestingly enough. There's actually people who are worried about depopulation, but because the growth rate has plummeted in certain, especially Western countries. But like back in the 1980s, there was fear of a population bomb, right? We thought that if human growth rate was unchecked, and unchecked, that's the key word right there, right? Then it would follow the J curve, and pretty soon we would have, like, let's say, I don't know, 50 billion people on the planet, and then the concern there is, can the ecosystem support it? Now that we are, by the way, the population bomb was supposed to have happened, I think the prediction was like 10 or more years ago, and now we're past it, and it hasn't quite happened. In fact, growth rates are starting to taper off, and some countries are actually worried about there's kind of this, like, if you guys have you guys ever heard of like the I forget what it's called, but they break down the population size. So this is like 0 to 10-year-olds, and then this is like 10 to 20-year-olds. And if you look at the makeup of the population of the country, this top would be like 80 to 90-year-olds. You'll notice that the majority of the population is constituted of younger people. But in countries like Japan, I think it's Japan and a few others. There might even be some European countries that are starting to see this. but they're starting to see an inverted pyramid where it's actually wider now at the top. You have all these old timers that are living super old, and then babies being born, not very many, right? So what the heck is going to happen to those countries where you've got a massive, and by the way, the problem is that this demographic up here depends on this demographic, right? Because this is the workforce is constituted by the younger generation, and then the retirees who depend on the workforce are way outnumbering the number of working people. So there's like countries that are starting to see the writing on the wall, and they're starting to worry a little bit. And I think, have you guys heard that they're like encouraging people to have babies more in those countries, or like even paying them or giving them tax break or something, trying to?
It's in a certain area though.
Do you know what country it is?
They do that in. I forgot if it's in Japan or.
I think it might be Japan.
Yeah.
That's what I'm thinking it was too. If I recall. So, anyways, that is a little. I will admit that's a little bit of a tangent from what I should be telling you guys about, but it reminded me of this, and so I wanted to talk about it. But anyway, when you look at your formula sheet, okay, so we're gonna go ahead and focus in on exponential growth because you guys are gonna calculate this today. In fact, so only occurs, by the way, when conditions are ideal. So this means that there is like no limiting factors. So that would be like unlimited food, unlimited oxygen. And by the way, I'm kind of, what I have in mind here is my aquarium, because there was a time, space, oxygen, food, what else would there be? Habitat. Anyway, let's say all of that was unlimited, which, by the way, at the earlier stages of population growth, at earlier stages, usually it is unlimited, right? So like when you first put the snail in the aquarium, which, by the way, that there was a time when this was snail free. There were no snails in there whatsoever. And then like one kid dropped this mesocosm in that had these invasive snails. And without thinking, he was like, "What do I do with this rock? Do you want it?" Like, it's the end of the year. I was like, "Oh yeah, just dump it in there." And I didn't even think about it, but he dumped it in there. From that day forward, we saw a population bomb of snails. Like it started with like one or two, and then there was this huge infestation where it was like just speckled with them everywhere. And then after that, it like dropped off. There was like a crash, and then it just kind of, and it's been like this now for a year or more, where the number of snails has just kind of found an equilibrium. And it's kind of just chilling there. And I mean, there's a lot. There's hundreds probably. But anyway, it doesn't seem to be going up or down. And but like I said, that very first snail, initially, it went crazy, right? And then it dropped off, and then it kind of leveled off. So this is like real life. Like in real life, it usually you have this like exponential at the beginning. And why is it exponential at the beginning? Well, because when there's only one of you, you have everything to yourself, right? These first few snails, they had no competition. They had like unlimited food, unlimited space, unlimited oxygen. But then pretty soon in here, actually, yeah, right about here, because this is where growth, this is where I guess you could say the growth rate stops increasing. Now, how do I know that? Because if you look at the slopes The slope here is getting steeper and steeper and steeper, and it's right at that point where the slope actually starts getting less steep. You guys see that? I forget what you would call that in math class, but it's just where the rate, because remember the rate is the slope, right? The growth rate. So it's at its steepest right there. That's the steepest rate, the highest rate. And then after that, it starts to actually taper off. So why is it right there at that point where the rate stops increasing and begins decreasing? Well, because this is where we're finally reaching carrying capacity. Capacity is reached. In fact, you can kind of see that this dot lines up with the carrying capacity over here. You see that? Carrying capacity is reached. So, what is it that actually causes a carrying capacity to exist? Limited space, limited oxygen, limited food. You can't have an infinite number of snails in that one aquarium. Okay, so this is kind of common sense. You probably know this already, but I know if you're like me, you're probably okay with this conceptually. This all makes sense. But then as soon as the math is brought into it, you're like, shoot. Okay, now the math, that's going to make it. I'll get these questions right. But as soon as they give me the math question, I'm probably going to miss that. I don't want you to feel that way because the math is actually really easy. Let me show you how. Okay. On your formula sheet, you will be given the following equation. Wow, actually, you might not be. Okay, no worries. I'm going to give it to you. R max, okay, which is the max, which is the, I guess you'd call that the growth rate. You have to calculate that by factoring in the birth rate, subtracting the death rate, and then you're going to divide by the original population size. So here's an example. Let's say, like, we could use the snails, I guess. We could say, let's imagine that every day, 20 snails are born. And every day, 4 snails die. And the original population size was, when the population size when this was occurring was, let's say, 10. So what I would have you do then is calculate the growth rate. So we would say, well, our max is going to be the birth rate, which was 20 minus 4. So 16, basically you're adding 16 per 10 snails that you have, right? And then that helps you calculate the rate. So 20 minus 4, 16, 16 divided by 10. Our max is 1.6 in this case. And that's a large growth rate because, I don't know, snails, they're asexually reproducing, so they're going to multiply pretty quick. All right, now here's where you have to be able to apply this. So now that you know your R max, which very often the multiple choice questions, they'll just give you R max. They'll just tell you what it is. They'll say R max is this. What would the population size be 5 days later? Something like that. So let's imagine for a minute that we've got, okay. You start with 10 snails. How many will you have Let's just do 3 days later. How would you calculate that? You start with 10. The growth rate is 1.6. How many would you have 3 days later? Okay, so here's the thing. The number of snails that get added depends on the population size. So what you can't do is just multiply 10 times 1. It's not as simple as just like a linear multiplication. So what you have to use is you have to use this formula where this represents the growth, and the growth is going to equal the R max times n, which is the population size. Okay, here's the problem though. The population size changes every day. So it's the growth is not going to be you're not going to be growing by the same number of snails each day. You're going to be growing by more snails each day. So here's how you would do this. You would say, okay, 0 days, 1 day, 2 days, 3 days. At 0 days, we were told that we have 10 snails because that's what we're starting with, right? So how many would we have 1 day later? Okay, well, we know our max is 1.6 times however many snails we have, and that's going to tell us the growth. 1.6 times 10, 16. We're going to grow by 16 snails. Okay, so how many will we have on day 1 after they've duplicated? 10 plus 16, 26, right? Because this is the how many new snails you'll have. How many new snails? Okay, so now we have to calculate the growth on day 2. Well, the problem here is that we have the same R max, but our population size is now 26. So we're going to grow by more than 16. We're going to grow by 42 this time. So if we grow by 42, what is our population on day 2? 26 plus 42, 68. Okay. Now what about on day 3? So do you guys see that we are growing by more and more each day? And so if you plotted that out, this graph growing by more and more each day, you would see a J curve, right? Be getting exponentially more and more. Okay, so between the second and third day, our growth rate is still the same. Our max is always 1.6, but we have a larger population, and so we're going to grow by even more. Wow, this time we're going to grow by 109. So if we have 68 and we grow by 109, wow, 177. Okay. So I have now answered the question. How many snails will you have 3 days later? 177. Any questions on that? All right, now you might be looking at this and saying, Mr. Roth, there's got to be an easier way to calculate this rather than going day by day. You're right, there is. There is an easier way. But I don't know why this is. But let's go back to that formula sheet. AP Bio does not give you the easy equation. They only give you what I just showed you. And so as your teacher, I'm a little bit torn as to whether or not I should even give you the bigger equation, because I'm anticipating all the questions you're going to get are going to have you utilizing this, which is like how much will it grow between this day and this day, right? But if you wanted to, then this is up to you. But unfortunately, I mean, I don't, there is no way for me to change the formula sheet. So you would just have to memorize this formula. And you could if you wanted to. But there's another formula like this: NT equals N times 1 plus R max to the T power. So let me show you how this gets us the same answer. We already know that the population is starting at 10. We know that R max is 1.6. So we're going to have 2.6, 1 plus R max to the third power equals, it should equal 177. And yes, it does. Well, 176. I don't know why it came out a little bit less, but whatever. Close enough. It's probably because we didn't use the full decimals or something. But this equation will also get you to the same answer. We plugged in the third day there for the exponent. We plugged in 1.6 for the R max. We plugged in the starting population of 10. So why does AP Bio not give you that? I don't know. I'm still scratching my head over that one a little bit, but if you want to like memorize that one, you can. So you can get to it either way. You can get to it by just doing 3-step, or you can just do 1-step and plug it in. Okay, any questions about that? All right, so now, just real quick here. Does everybody recognize that this model of exponential growth, where you've got unchecked, completely unchecked growth, right, where it just goes to infinity, is never the way that it is in nature, right? At some point, the growth slows down because there's disease, there's a famine, right? You run out of food, you run out of space. So this is what it will always look like. It'll always look like this. Real life, right? Real life always looks like that. So there's a word to describe this kind of growth, and it is called logistic growth. And we already kind of saw what that would look like, but you'd have this initial exponential, and then so it forms, well, actually, hang on. A perfect logistic curve wouldn't even have the hump. It would look like this. Perfect logistic growth would look like that. And this would be the theoretical carrying capacity. Okay. But again, this still has the same features. Right here, this is the point where growth rate begins to decline. This is the point where the slope, the steepness, begins to decline, which is the growth rate. So this must be the point where competition is starting, or this must be the point where food is starting to run out, right? Okay, so here's what you need to know about this. This particular kind of growth has an additional factor. So when you look at the formula, so let's compare the formulas. Exponential, you have the amount of growth is going to depend on the R max times whatever the population size is. Logistic will be the same as that. It's going to be the R max times whatever the population size is, times an additional factor. So it's this piece here this k minus n divided by k. This piece here is the logistic factor, you could call it. And if you're a mathematically minded person, this will make sense. If you're not mathematically minded, you might be like, okay, whatever you say, Mr. Roth. I don't really care how the formula works as long as I can use it. I know some people are like that. That's fine. But if you want to know how the formula works, this term, right? In math class, you guys call it a term, right? This term, this k minus n divided by k term, this term gets, I gotta think here before I speak. I don't want to mess this up. This term changes as n changes. Now, what is n? N is just the population size. So here's how it changes, right? K represents the carrying capacity. Let's just say it's 50. Carrying capacity is 50. As if K is 50, as N gets larger, the term gets smaller, right? So what this is going to do, if this term here is getting smaller, it's going to, as this term gets smaller, it reduces growth. It reduces the overall growth, right? Because when you're multiplying this term by this term, and this term is getting smaller, it's going to make the growth less and less. And that's what's happening right here, right? The growth is starting to taper off. And it's all this logistic factor term that's causing it to do that. When you don't have this term, like up here, where you just have the R max and the N, then there's nothing to reduce the growth, and so it just goes exponentially up. All right. That might be a little bit more than you wanted to know, but it's fine. I mean, if they're not going to ask you like real crazy details. They just want to make sure you can apply this. So let's have you guys apply it. I'm going to give you this practice. We're going to see